Good morning everyone. Today I am going to discuss about the computer organization subject unit 2. Coming to the content. So these are the content we are having in the unit 2. So this is the second part of the unit 2. So these are the topics: stack organization, instruction formats, addressing modes, data transfer and manipulation, execution of a complete instructions, sequence of control signals, program control. So these are the different topics we are going to explain in the unit 2 second section. So coming to the introduction. So in this introduction we are going to explain about the CPU. So and we are going to explain the major parts of the CPU. So the main parts of the computer that performs the bulk of data processing operations is called central processing unit, and it can be referred as a CPU. So in this CPU we are having the major parts. So these are the major parts. So control unit, register set, arithmetic, logic unit. So these are the three major components are available in the CPU. So what are the use of these components? What are the operations will be performed? These three major components means. So in this register set, this register set will store the intermediate data used during the execution of the instructions. So that is will be performed by the register set. Next, arithmetic logic unit. So arithmetic logic unit ALU will performs the required micro operations for executing the instructions. And next, coming to the control unit. So it supervises the transfer of information among the register set, and instructs the ALU as to which operates to perform. So this is the three components performance of the CPU. Okay. So coming to the stack organization. So what is mean by stack organization? A stack or lost in first out. A stack organization is nothing but a stack or lost in first out is useful feature that is included in the CPU of the most computers. So what is mean by stack organization? We can say it is a lost in first out, and we can say it is a stack. It is useful. It is mainly useful. It's useful for features that is included the CPU and included in the CPU of the most computers. So the stack is nothing but the stack is a storage device. The stack is a storage device that stores information in such a manner that items stored last in first item retrieved. Okay. So what is mean by stack ma? Stack is a storage device. Stack is one storage device. We are going to store the information. So we are storing the information in the form of lost in first out, lost in first item retrieved. The operations of the stack can be compared to a stack of trays. The last tray placed on top of the stack if the first to be taken off. In the computer stack is a memory unit with an address register that can count the address only. The registers that holds the address for the stack is called stack pointer. It always points at the top item in the stack. The two operations that are performed on stack are the insertion or deletion. So already we have some diagram about this stack organization. So I mean so I having some storage devices. In these storage devices, whatever the information I am storing, that information is stored in the form of lost in first out. So lost in first out. So lost in first out is nothing but, so whatever the lost item, lost in first out, it means whatever the lost data we are representing, that can be removed first. Okay. Inserting in the last and removing in the end of the stack. So the operations of the stack can be compared to the stack of trays. So the last tray placed on the top of the stack is the first to be taken off. In this computer stack is the memory unit with an address register that can be count the address only. So the register that holds the address for the stack is called the stack pointer. It always points the top item in the stack, in the top item in the stack. Whatever the two operations that are performed on the stack are the insertion and deletion. Okay, so these operations of insertion is called push. We can say insertion is nothing but we are pushing the data into the stack, and if you want to delete the data, that is called pop. Okay, if you want to delete or remove the data from the stack, we can say it is a pop. Push or pop operations will be performed. In other way, we can say insertion or deletion. So these operations are simultaneously by incrementing and decrementing the stack pointer registers, incrementing and decrementing the stack point registers. So next coming to register stack. So what is meant by register stack? The stack can be placed in the portion of a large memory, or it can be organized as a collection of finite number of memory words or registers. So a stack can be placed in the portion. So this is the diagram. So this is the stack. So this is the stack, and we can say it is a 64 word stack. Okay. So this is the storage block diagram of the stack. In this we can store 64 words. Okay, so from 0 to 63 we can counting. So overall we count means it is a 64 word stack, and in this we are going to insert. SP means stack pointer. Okay, so here we are pointing at the C. So a stack can be placed on the portion of a large memory, or it can be organized as a collection of finite number of memory words or registers. Okay, so in the below figure we are having, this is the below figure. So this is the diagram, main diagram. In this stack pointer, the stack pointer register SP contains a binary number. The stack pointer register SP contains a binary number whose value is equal to address of the word. It is currently on the top of the stack. 3 items are placed in the stack. In this stack we are placing the 3 items, that is stack A, B, C in order. In orderly we are placing A, B, C. Okay, so in this figure C is the top of the stack. C is the top of the stack. So now in orderly I am placing the 3 stack items in the stack A, B, C. At the top of the stack we are placing the C. Okay, so the top of the stack, so that the content of SP is 3. In the place of 3, what the value we are having, C. Okay, so for removing the top item, the stack is popped by reading the memory word. So if you want to remove the top item of the stack, that is C. Okay, I am popping that data by reading the memory word at address 3 and decrementing the content of SP stack pointer. Now the top of the stack is B. When I remove the top of the stack C by using the address 3 in SP, so I popping that data. Now what is the top of the data now? B. Okay, the stack of the top of the data is B. So the content of SP is 2. Okay, stack pointer is 2. Okay, and similarly if you want to inserting a new item, the stack is pushed by incrementing SP and writing a word in the next higher location in the stack. So if you want to, it means what, I want to insert a new item, I want to increment the stack values. So I am going to insert the data in the SP, then I will be insert the new item D. Okay, so the top of the item will become the D. That's like, okay. So in a 64 word stack, the stack pointer contains 6 bits because 2 power 6 is equal to 64. Since stack pointer has only 6 bits, it cannot exceed a large greater than 63 in binary. So when 63 is incremented by 1, the result is 0, since I am using the 1 1 1 1. So this is the explanation whatever we are having here. So this is in a 64 word stack, the pointer contains the stack pointer contains the 6-bit because 2 power 6 is equal to 64. So this is not 26 ma, this is the 2 power 6 is equal to 64. When 63 is incremented by 1, the result is 0, since the value will be represented this like 1 1 1, triple ones triple one, okay, plus 1. So is equal to 1 0 0 0 0 0 in a binary format. But SP stack pointer can accommodate only the 6 least significant bits. Then the 1-bit register. So the 1-bit register full is set to 1 when the stack is full. Similarly, when 0 0 0 0 0 is decremented by 1, the result is 1 1 1 1, and then the 1-bit register is empty. Is set 1 when the stack is empty of items. So in this we are having the DR. So in the diagram I am having the DR. This is the DR. So the DR is the data register that holds the binary data and that to be written into or read out of the stack. So next, coming to push. What is the use of push? So initially SP stack pointer is clear to 0. Stack pointer is clear to 0. So if you see the diagram, so this is the diagram, stack point is clear to 0. Empty is empty in the upper side. See my in SP pine chuste empty undi. So empty is a set to a 1. Empty I am providing here 1, and full is clear to 0. And so that SP points to the word. SP points to the word at the address 0. So SP will be points at address 0, and the stack is marked empty. The stack is marked empty and not full. So what is mean by empty? If we keep 1, if we set 1 at the empty and full is become 0, and SP become SP will be points at the SP means what? Stack pointer will points at the address 0, then the value of the address stack is 0. It is not full. Okay. So if the stack is not full, if full is equal to 0, a new item is inserted with a push operation. A new item is inserted in the push operation. Push is nothing but inserting a new information into the stack. So the push operation is implemented with the following sequence of micro operations. How we are pushing? So SP pointer. SP is means stack pointer gives rise to SP plus 1. SP means what? Stack pointer plus I am adding the incrementing the stack pointer. So that is plus 1. So in the stack pointer, okay, in the stack pointer, so gives rise to data register. So stack pointer, write the item on the top of the stack. At the top of the stack I am going to write the item. So if SP is equal to 0, then full gives rise to 1. Check if stack is full. So at the stack pointer I am providing the 0, at full I am giving the 1. Empty is becoming 0. So the stack not empty. Now the stack is not empty. I am inserting some value in the stack. So that is the stack pointer is incremented so that it points to the address to the next higher word, and the memory write operation inserts the word from DR to the top of the stack. So in this first item stored in the stack is at the address. The last item is stored at address 0. If SP stack pointer reaches 0, the stack is full of items. So if full is to 1. Once item is stored in the location 0, there are no more item registers in the stack. So empty is clear to 0. So this is called the push. Okay. So this is the formation of push the data into the stack. Next, coming to the pop. So what is mean by pop? If you want to delete the data in the stack, if you want to delete the data from the stack, we are using the pop or deletion. So a new item is deleted from the stack if the stack is not empty, if empty is equal to 0. So stack in the stack we are having some information, so that information is need to delete. So what are the topmost item is there in the stack, we have to delete that item. So the new item is deleted from the stack if the stack is not empty. So the pop operation consists of following sequence of minimum operations. So dr gives rise to m of sp, stack pointer. We are going to read the item from the top of the stack. So now I am going to decrement the value from the stack pointer. So that is why I am going to giving the minus operation, that is sp minus 1. I am going to decrement, I am going to delete the data from the stack. So I am going sp minus 1. Okay. If sp is equal to 0, then item gives rise to 1. Check the if stack is empty, then stack is empty. Full is equal to 0. If we provide full is equal to 1, then our stack is full. If we provide full is equal, full gives rise to 0, the stack is not full. Okay. So empty is 1, check the stack is empty. If empty is 0, the stack is not empty. Okay. So this like the difference we can say. Okay. And so in this stack pointer is then decremented. If its value reaches to 0, the stack is empty. So empty is said to be 1. So this condition is reached if the item read was in location 1. Once this is read out, sp is decremented and reaches the value 0, which is the initial value of sp. And next coming to memory stack. So what is meant by memory stack? In the above discussion, a stack can exist as a standard alone unit, but in the CPU implementation of a stack is done by accessing a portion of memory to the stack operation and using a processor register as a stack pointer. So the below whatever the figure we are having, it shows a portion of a computer memory partitioned into 3 segments, that is program, data and stack. Okay. And this is the diagram we are having. So this is program, data and stack. These are the 3 portions we are doing in this computer memory. So what is the main working of this? So in this program counter, PC means here we are having PC and AR and SP. What is mean by PC means program counter. The program pointer, it points the address of the next instructions in the program. AR means address register, that points to the array of the data, and SP means stack pointer, that points to the top of the stack. And so in this 3 registers are connected to a common address bus. Three registers are connected to a common address bus, and either one can be provide an address for a memory, that is PC. So PC is used during the fetch phase to read an instruction. AR is used during execution phase to read an operand. PC means program counter. It is mainly used for during fetching the phase to read an instruction. AR means address register. It is used for during the execution phase to read an operand. SP means stack pointer. It is used to push or pop the items into the stack into or from the stack. Okay. And this is the PC, AR and CP. Okay. Next, the item in the stack communicate with the data register. So the items in the stack communicate with the data register DR. Okay. So a new item is inserted with the push operation. A new item is inserted with the push operation. If you want to insert a new operation, we are using the push operation as follows: SP minus 1. So in the stack communicate with the data register DR, a new item is inserted with push operation as follows. So SP gives rise to SP minus 1. is minus 1 means we are going to decrement the value. M of SP gives rise to DR. The stack pointer SP is decremented so that it points at the address of the next word. The memory write operation inserts the word from DR into the top of the stack. So a new item a new item is deleted. A new item is deleted with a pop operation as follows. This is dr gives rise to m of memory of stack pointer, sp gives rise to sp plus 1. Sp plus 1 we are going to increment the data. So the top item is read from the stack into dr. The stack item is read from the stack into dr. The stack pointer is then decremented at the point at the next item in the stack. Most computers do not provide hardware to check the stack overflow or underflow. Overflow means full stack, underflow means empty stack. So the stack limits can be checked by using processor registers. One to hold the upper limit 3000 in this case. Okay, other to hold the lower limit, it is 4001 in this case. So the two major operations need for either push or pop or an access to memory through SP or updating the SP. Okay, these are the push or pop two micro operations. So next coming to reverse the polish notation. So in the stack organization is very effective for evaluating arithmetic expressions. The common arithmetic expressions are written in infix notation with each operator written between the operands. So we are considering some simple arithmetic expressions, that is a into b plus c into d. So this is one simple arithmetic expressions. So okay, in these expressions we are first evaluating. So in these expressions, for evaluating the above expression, it is necessary to compute the product a into b and store this product result while computing c into d and sum the and then sum the two products. So first what we have to do? First we have to calculate the a into b. After that we have to evaluate the c into d. After getting the two values, we are going to do sum. Between that two values we are having the plus operations, we are performing the product sum operations, sum of two products. Okay, so for doing this type of infix notation, it is necessary to scan back and forth along the expressions to determine the next operations to be performed. And in this Polish mathematician showed that arithmetic expressions can be represented in prefix notation. So this representation referred to as a Polish notation. We are places the operator before the operands, so it is also called as prefix notations. So in this postfix notations referred as a reverse Polish notation, place the operator after the operands. We are having this infix. Infix means middle of these two operands we are providing the operator, then it is called infix notation. In front of the operand we are providing the operator, we can say it is a prefix. Okay, we are providing the prefix. Okay, before I am providing the operator, before the operand we are providing the operator, that is called prefix or Polish notation. After the two operands we are providing the symbol, operator, we can say it's a post or reverse Polish notation. So the reverse Polish notation is in the form of suitable for stack manipulation expressions. So it is by a into b plus c into d. So this is the normal expression. For this expression I am providing the reverse Polish notation, that is A into AB into CD into plus. This is the reverse Polish notation. So like that I am writing the reverse Polish notation. Okay. And we are going to evaluate and scaling this expression from left to right when an operator is reached and perform the operation with the two operands found on the left side of the operator. So remove the two operands and the operator and replace them by the number obtained from the result of the operation. So we are going to continue to scan the expression and repeat the procedure for every operation encountered until there are no more operators, until there no more operations. Okay, and no more operators. So in this we are having the evaluation of arithmetic expressions. So in the reverse Polish notation we are going to combine with a stack arrangement of register is most efficient way known for evaluating arithmetic expressions. This product this procedure is employed in some electronic calculators or also in some computers. So this numerical example may clarify this procedure considering the arithmetic expression 3 into b. So 3 into 4. So whatever the simple example we have seen in the previous, so like that only we are providing the values here. So reverse Polish notation combined with a stack management of the registers is the most effective way known as evaluating the arithmetic operation. In this procedure, so we are going to have some electronic calculators and also in some computers. The following numerical examples may clarify this procedure. We are considering some arithmetic expressions, that is how we are representing the previous example, A into B plus C into D. That's like only we are representing the values here, 3 into 4 plus 5 into 6. So this is the normal arithmetic expressions. First we are going to evaluate first 3 into D, 3 into 4. After that we are evaluating the 5 into 6. After getting that product values, we are providing the sum of two products. Okay now, so in the reverse Polish notation, we are providing the expression 34 into 56 into plus. This is the reverse Polish notation. So it means 3 into 34 means 34 after we are providing the operator, 56 after that we are providing the operator, after that we are providing the sum operator. So this is the reverse Polish notation. So whatever may be in the arithmetic simple arithmetic expression, how we are representing the evaluation of that like only we are expressing that reverse Polish notation also. Okay na? But in the we are just providing the operators after the values. Okay, so that however we are provided, the operation is evaluated in the form of 3 into 4, 5 into 6. After that, getting the two values, we are providing the sum operation. Okay na? So this is the stack operations. Okay now, so this is the diagram of stack operations. We are going to evaluate the 3 into 4 plus 5 into 6. So first we are inserting the 3 value. Okay, After that, first how we are evaluating. First we are evaluating the 3 into 4 value. First I am inserting in the stack 3. After the stack, after that 3, I am inserting the 4. So in the first place we are having 3, or the second place on the top of the stack we are having the 4. So we are providing the product, and means into operation we are providing product operation. It means 3 into 4 how much? 12. So whatever the our operation 12. Okay. So in the stack we are having value 12. So next, what are the next operation? 5 into 6. We have to evaluate these two values. So I am inserting the 5. I am pushing the value 5 in the stack. After that I am pushing the value 6. Now I am providing the product operation. 5 into 6 how much? 30. 5 6 are 30. So after that 30, after the first product value is 12, second product value is 30. After that, for these two product values I am providing the plus operation, I mean sum operation. So that is what? 42. Okay. So 30 plus 12 how much? 42. So this is our result. This is the evaluation of this expression. Okay. This is the arithmetic expression. Next, coming to the instruction format. What is meant by instruction format? So in this instruction format, the formats of an instruction is usually depicted in a rectangular box symbolizing the bits of the instruction as they appear in the memory word, or in a control register. The bits of the instructions are divided into groups called fields. So the common fields found in instruction formats are one operation code field that specifies the operation to be performed, and an address field one is code field that specifies the operations to be performed, and another is a address field that designates a memory address or a processor register, and mode field that specifies the way the operand or effective address is determined. Okay, these are the different fields of the instruction formats. Okay, and most computers fall into the three types of CPU organizations. One is simple accumulator organization, general register organization, stack organization. These are the three most types of CPU organizations. So what is meant by simple accumulator organization? In an accumulator type organizations, all the operations are performed with a implied accumulator register. So the instruction format in this type of computer uses one address field. For example, the instruction that specifies an arithmetic addition and field defined by the assembly language instruction as add x. Okay. So where x is the address of the operand, and add instruction in this case results in the operation AC, accumulator gives rise to accumulator gives rise to AC plus m of x. AC is the accumulator register, m of x symbolizes the memory word located at address x. Okay. So this is called the single accumulator organization. Next, general register organization. The instruction format in this type of computer needs 3 register address field. Thus the instructions for the arithmetic addition may be written in an assembly language as add R1, R2, R3. So we are going to denote the operations R1 gives rise to R2 plus R3. So the number of address fields in the register instructions can be reduced from 3 to 2 if the destination register is the same as one of the source register. Thus the register's address R1, R2 would denote the operation R1 gives rise to R1 plus R2. Only register addresses for R1 and R2 need be specified in these instructions. The general register type computers employ 2 or 3 address fields in their instruction format. Each address field may be specify a processor registers or a memory word. An instruction symbolized by add R1 X would specify the operation R1, and R1 one implies R1 plus M of X. So it has two address fields, one for register R1 and other for memory address X. So this is the general register organization. Next, stack organization. So what is meant by stack organization? A stack organized CPU has push or pop instructions which required to be address field. Thus the instruction push X will push the word at address X to the top of the stack. So the stack pointer is updated automatically. Operation type instruction do not need an address field in stack organized computers. So whatever the instructions add is there, that add in a stack computer consists of an operator code only, no address fields. The operation has effect of popping the two top numbers from the stack, adding the numbers and pushing the sum into the stack. There is no need to specify the operands with an address field since all operands are implied into be a stack. So most computers falls into the three types of organizations. Some computers combine the features of more than one organizational structure. So we are going to influence the number of address on a computer programs. We'll evaluate the arithmetic statement. So arithmetic statement, that is x is equal to a plus b into c plus d. Okay. So next, coming to three address instructions. What is mean by three address instruction? In these three address instructions, formats can be use each address field to specify either a processor registers or a memory operand. So in this program we are having the assembly language that evaluates x is equal to a plus b into c plus d. So as shown in the figure, we are having together with components with that explain the register transfer operations for each instructions. So this is add. So these are the different instructions, three instructions. We are going to add the instructions. So add R1 comma A comma B. So it means what? In the R1 register, in the register 1, we are adding A plus B, memory M of A plus M of B. Okay, we are adding the values in the register. Next, add R2 CD. Okay, so in the register R2 we are going to add the CD values. So multiply X comma R2. It means we are going to multiplying the two operators, that is two operands, that is R1 into R2 in the X address. Address is the X. In that address I am going to store that value. So this is the three instructions, address instructions we are having. Okay. So next, two address instructions. What is meant by two address instructions? Format uses each address field can specify either a processor register or memory word. The program can be evaluate x is equal to a plus b into c plus d is as follows. So how we are representing this one? Move. We are moving the value. We are moving the data into the register R1. It means in the R1 I am going to move the data A. Okay. So A information is moving in the register R1. Okay. Next, add means what? R1 B. R1 B means what? In the register R1 I am going to add the register value and B value in the R1. Okay. Move R2 RC. Next I am moving the value C value. Okay. Okay, I am going to moving the next C value. After that I am adding the D value to C. So the C value and D value both are added, and whatever the sum is representing in that, it will be stored in that R2. After that I am going to multiplying the R1 and R2. R1 means what? A plus B value, whatever the information we are doing addition, that value will be represented in the R1, and C plus D value is doing addition, that value is available in the R2, and we are providing the product operation between that, and the value is stored in the X X is the address, in that R1 value is stored. So this is the two address instructions. Okay. Next, coming to one address instructions. This is the one address instructions. In this one address instruction uses an implied accumulator registers for the all data manipulation. For manipulations and divisions, there is no need for a second register, but for the basic discussion, we will neglect the second register and assume that accumulator contains the result of the all the operations. So x is equal to a plus b into c plus d is how we are representing. First, I am going to load the a value in the accumulator. So accumulator is the register value. In this accumulator I am going to store the a value. After that I am going to add the b value in the accumulator. So accumulator lo manaki em undi already a undi. So a ki manam em add chestunnamo b anedi add chestunnam. So it means I am going to providing the addition operation between a plus b. Okay, a ki b ki madhya I am going to provide the sum. Okay, after that I am storing the value in the t. Okay, so whatever the information available in that accumulator, that is stored in the t. After that I am loading the c value. After that adding the d value to the c, and the c plus d will be added and stored in the AC. Okay, after that I am providing the multiplication between the a plus b and c plus d. It means accumulator plus m of t. Okay, both are added and stored in the x value. So this is the one address instruction. So next, zero address instruction means what? A stack organization computer does not use an address field for instruction add and multiple. The push or pop instructions, however, need an address field to specify the operand that communicates with the stack. The following program shows x is equal to a plus b into c plus d will be written for a stack organized computer. So this is the push. We are pushing the a value. Toss, toss means what? Top of the stack. At the top of the stack we are pushing the a value, and of the top of the stack again I am pushing the b value, and after that both a value and b value I am going to provide the addition. So I am going to add operation, that is at the top of the stack we are going to add the a plus b value. Again I am pushing the c value, again I am pushing the d value. After that I am adding the top of that stack, that is c plus d. After that multiplication, the top of the stack c plus d into a plus b, both are going to multiply that value. After multiplying that value, that product will be stored in the x value, that is called pop. So these are the zero address instructions. Next, RISC instructions. What is meant by RISC instructions? What we have in the RISC instructions? The RISC instruction is a set of typical RISC coprocessor is use only load and store the instructions for communicating between the memory and the CPU. All other instructions are executed within the register of CPU without referring to memory. So load and store instructions that have one memory and one register address, and computational type instructions that have three address with all three specific processor registers. We are having some program to evaluate, that is x is equal to a plus b into c plus d. So this is the loading. We are going to load the register R1A and R2B, and we are loading the R3C, and after that we are loading the R4D. So after that three values, whatever the values we are loaded in A, B, C, D, both are added, R1, R1, R2, R3, R3, R2. So this is like we are going to adding the values after we are providing the multiplication operation between the two addition values. After that we are going to store that value in the X. So this is we are loading the instruction transfer that operands from memory to CPU register. The add and multiply operations are executed with the data in the register without accessing memory. The result of the computations is then stored memory with within a store or in the instructions. Okay, so this is called the RISC instructions. So up to here we have discussed about the RISC instruction. In the next class we will continue the next topic and thank you everyone.